Welcome back. In this section, we're introducing another family of functions called the logarithmic functions. So, probably not as a surprise, I emphasized in the last section, talking about exponential functions, how exponential functions are all one-to-one. And one thing, of course, you should remember from 6.2 is that if you have a one-to-one function, then it must have an inverse. So our big conclusion here is that every exponential function should have an inverse. So if you had a function y equals a to the x, there should be some other function out there that switches all of the x and y values. The function that does this is called a logarithmic function. So for any exponential function with base a, there should be a logarithmic function also with base a that is its inverse. So the logarithmic function with base a, we write that as log with a little subscript of a. So here, log a, that's the name of our function. And the logarithmic function with base a switches, again, the x and the y values for our function. So, for example, if you happen to know that a to some power of y gives you x, then that means the logarithm for x should give you that y. In other words, if you know something as an exponential equation, so for example, here's a number fact, 5 to the power of 3 is 125, the logarithmic function will switch the input and the output. Here the input was 3, the output was 125. So for a logarithm, you'd have the input of 125 and the output of 3. So this is the key idea here, that for an exponential function, the power was the input, and for a logarithmic function, the power is the output. 5 to the power of 3 is 125. Here, the 3 was the input. For the logarithm, what comes out of the log would be the power. So when somebody says, what is log base 5 of 125? They're asking you, 5 to what power gives you 125? And the answer is, the power is 3. So that means anytime that we have an exponential function or an exponential equation, we should be able to rewrite it as a logarithmic function or logarithmic equation. So now, let's take a look at this example here. We've got an equation 3 to the power of x minus 1 is equal to 7, and we want to rewrite that as a statement involving a logarithm. And so remember that since this is 3 to the power of x minus 1, my base is 3, then as a logarithm, it would be a log with base 3. And that the logarithm will switch the input and the output. For my exponential equation, x minus 1 was the input, so for my logarithmic equation, x minus 1 should be the output. For my exponential equation, 7 was the output, so for my logarithmic equation, 7 is the input. Again, I want to be clear here just as far as notation goes, because this is different than something we've seen before. You might think that there's something that needs to be done algebraically, combining the 3 and the 7, and the answer is no, there's absolutely nothing that we have to do with the 3 and the 7 to combine them together in any sort of a way. The log base 3, that's the name of our function, and 7, that's the input for our function. Just like in the same way that you might write f of 7, where f is the name for the function and 7 is the input. You don't have to combine the 7 and the f somehow, doing some sort of work with combining letters and numbers. It's just f is the name of your function and 7 is what's going into that function. Similarly, we don't need to combine the 3 and the 7 in any way, because log base 3, that's the name of our function, and 7, that's what's going into our function. You might sometimes see me writing it with brackets to make that really clear. So I might sometimes write this as log base 3 and then put in brackets 7. I don't always write that because usually if it's only a single number or a single term, then it's also pretty clear that it's log base 3 of 7. I will sometimes use brackets if I'm talking about an input going into a logarithmic function that's more than just a single number. So, for example, if I had a log base 3 of x minus 2, to make sure that it's clear that the x minus 2 is all going into that logarithm, I might put brackets around it. But if I'm just talking about log base 3 of x, I may or may not put brackets around the x, and those are both equivalent. So writing log base 3 of x or log base 3 with brackets around it x, those both mean the same thing. So sometimes I'll use brackets to help me make my writing clear as to what exactly is going into the logarithm. But for this one, I think it's clear enough to just say log base 3 of 7. Same sort of thing with the last one here. We have this log base 5 of 3 minus x equals to 2. And you want to rewrite it as an exponential equation. So that means instead of log base 5, it'll be 5 to the power of. It'll be the same base, but we're going to switch our input and our output. For the log equation, the output was 2. So for the exponential equation, the input will be 2. For the log equation, the input was 3 minus x. So for the exponential equation, the output would be 3 minus x. I just want to point out the whole purpose of why we have logarithms, and I think these two examples kind of make it clear. If you were interested in solving this equation for x, you would have to get the x out of the power. And the way that you would do that would be to write it as a logarithmic equation. At that point, you could move the 1 to the other side, and you would have solved for x. Similarly, if you had a logarithmic equation and you wanted to solve for x, you would need to get this 3 minus x out from inside the logarithm, and how you would do that would be to rewrite it as an exponential equation. Once it's in this form, you could just move the x and the 3 around, and you would have solved for x. So this will be a common theme throughout the rest of this chapter, that if we have an exponential equation, I'll use logarithms to solve it, and if I have a logarithmic equation, I can use exponential functions to help me solve it. I do want to be really careful, though, as far as notation goes, because this is a place where new mistakes get generated. And this is because we're seeing what looks like different functions, something that's different to what we're used to. And so sometimes people will make mistakes because of not understanding the notation. And one key mistake is this. When I write something like log base 5 of 125, typically there will be a few people who will say log multiplied by 125. And that's not just wrong in terms of words. It's wrong as a concept, that this is not two different things that are being multiplied together. This is not one thing multiplied by another. This is one function where 125 is the input going into this function, and this function's name happens to be log base 5. The reason why thinking about it as multiplication is a problem is because you might be now tempted to think that you can do some canceling. For example, I have seen people see things like log base 2 of 8 over 8 and think that the 8s can cancel, which that is not correct. The reason it doesn't work is 8 is not a factor of this numerator. 8 is not something that can be divided out of log base 2 of 8. So, unfortunately, that means that those 8s could not be canceled. Similarly, I'll sometimes see something like this, log base 2 of 8 over log base 5 of 8, and sometimes people will cancel the 8s and say that the answer is log base 2 over log base 5, which is wrong. Or even more wrong would be to cancel the logs and say that 2, 8 over 5, 8 somehow or now is the same thing, which of course is also wrong. Or worse, canceling all of that and just leaving it as 2/5, extremely wrong. So if we're thinking about these, log base 2 of 8, that's one single entity. Log base 2 of 5, log base 5 of 8, that's its own single entity. It's not two things multiplied together. And because it's not two things multiplied together, the 8 is not some sort of a common factor that can be canceled out. Kind of in the same way, if you're thinking about this, how if you were asked to find f of 3 over g of 3, you would not be able to cancel the 3's and say, oh, this is somehow now just f over g. That the 3's are numbers that are going into those functions. Those are not separate factors that can be canceled out. And similarly, if I asked you f of 2 over f of 5 for some function, you wouldn't cancel the f's. So in the same way, you wouldn't cancel the logs. All right, so we have not talked about evaluating logarithms, and we can, for some of them, find the exact values directly. And so for these, again, we have to remember that what a logarithm will give us as an output is a power. So when I say log base 3 of 9 is equal to what mystery number, that's equivalent to asking the question 3 to what power is equal to 9. So if we're thinking about it that way, thinking about that all of these log questions are really equivalent to asking an exponential question, just one where we don't know what the power is, we can now answer all of these. If you wanted to know log base 3 of 9, that would be 3 to what power gives you 9, and we know that the power is 2. So in other words, 3 to the power of 2 gives me 9. Similarly, log base 2 of 1/8, 2 to what power gives me 1/8? 2 to the power of -3. So here I'll write the equivalent fact below it. That's 2 to the power of -3 gives you 1/8. So log base 2 of 1/8 gives you -3. Log base 7 of 1, 7 to what power gives you 1? We know that 7 to the power of 0 gives me 1, so that means log base 7 of 1 should be 0. Log base 15 of 15. 15 to what power gives me 15? I know 15 to the power of 1 gives me 15, so log base 15 of 15 should be 1. Log base 2 of 2 to the 5. 2 to what power gives you 2 to the 5? The power happens to be 5. Since 2 to the power of 5 is 2 to the 5, then 2 to the power of 5 is 2 to the 5. Log base 2 of root of 2. That's the same thing as asking what's log base 2 of 2 to the half. Or in other words, 2 to what power gives you 2 to the half? What's the power? The power happens to be a half. A couple of things just to notice here, and these are things that will be true later on. One is this little fact in part C. We looked at log base 7 of 1 being equal to 0, but we'd see that it would be equal to 0 even if the base were different. If I said, what's log base 6 of 1? That would be 6 to what power gives you 1, and we know 6 to the power of 0 gives me 1, so log base 6 of 1 would be 0. In fact, in general, no matter what the base happens to be, for any base a, log base a of 1 would be 0 because a to the power of 0 would be 1. We have a similar sort of fact that we can also get out of part D, which is we see log base 15 of 15. That is a similar sort of statement we can make about log base anything of anything. So for example, if I had asked you instead, what is log base 7 of 7? that would be 7 to what power gives you 7, and the power would be 1. And in general, it's not just log base 7 that does this, it would be log of any base. So log base a of a is equal to 1 because a to the power of 1 is equal to a. And the last little fact that we hopefully might have noticed here is that if we have log base, in this case, 2 of 2 to a power, that was just the power. Log base 2 of 2 to the 5 was just 5. Log base 2 of 2 to the half is just a half. And that's not true for just base 2, that's true for any base. That log base a of a to the x is equal to just x. And that is because we have an exponential function put inside of a logarithmic function. Remember, we had that one property that was for any inverse function, that f composed with f inverse should be equal to x. That's exactly this property in action. We have an inverse function put inside of a function, and they cancel each other out. Okay, there are two special kinds of logarithms that we're going to introduce, and they have applications in science, and they also are important as far as coming up with approximate values. Two special kinds of logarithms, two special bases. One is the common logarithm, that's log base 10. And so for that, the common logarithm, we typically write it as just log, no base. So if you see, for example, somebody writing log of 7, what they actually mean is log base 10 of 7. The other kind of logarithm, which is sort of an important one, is log base e. Remember, e is Euler's constant, 2.718, and so on. Log base e, the natural logarithm is what it's called. We write that normally as ln. I do want to be careful here, and this is something for anyone who's taking other courses in the future, maybe using other books from other countries, which is this notation of log x, meaning the common logarithm. That's typical in North America. So in Canada and US, you'll often see that as a notation, that log x means the common logarithm. You'll sometimes see in some European countries, Germany in particular, where log is actually used to mean the natural logarithm. So if you're doing other advanced courses in mathematics later on, depending on where your book comes from, that little bit of notation may be different. But for most books that are published in North America, this is the standard way of writing things, that when you see a log with no base, it means log base 10, the common logarithm, and ln, that means the natural logarithm, log base e. So both of these exist on our calculator, and most calculators that you'll buy that have scientific functions will have a button for natural logarithm as well as for the common logarithm. So if you're taking a look at your calculator, you'll see that the button that we used for the exponential function, e to the power of, that is your natural logarithm button. ln is what's on it. And so if you wanted to find the exact value of natural log of 3, you would just have to enter ln and then 3, and we'd find that the approximate value for natural log of 3 is about 1.0986 or 1.099 if we're rounding it off to 3 decimal places. And then just to the left of that button, the natural log button, you'll see log, and that's log base 7. Oh, sorry, log base 10 rather. So if we wanted log base 10 of 7, we would enter log and then 7 and equals. And log base 10 of 7, that's about 0.845. So we can come up with approximate values for natural logarithms and for common logarithms. We'll see that there's a way for us later on to come up with approximate values for any logarithm with any base. But for now, we have those two that we can find approximate values for if we need them. So some things that we should know automatically as far as graphs go, as far as the graphs of our functions for logarithms and exponential functions. You know that for an exponential function, the domain was all real numbers and the range was positive numbers. So that means for a log base a, it should have the reverse. The domain is positive numbers and the range is all real numbers. You also know that an exponential function had a horizontal asymptote y equals 0. So that means a log function should have a vertical asymptote x equals 0. You have that an exponential function has a single y-intercept 0, 1. So that means that the logarithmic function should have a single x-intercept 0, 1. All right. So one thing that we can do right now, if we wanted to find the domain of this logarithmic function, is we know that for this to be defined, we would need x squared minus 5x plus 6. We would need the inside of that logarithmic function to be larger than 0. So really, when we're finding the domain of a log, it's going to come back down to solving an inequality. In this case, where is x squared minus 5x plus 6 greater than 0? So this is one where I'm going to solve just by graphing. If I were to look at y equals x squared minus 5x plus 6, I know that that would be a parabola. And it's a parabola opening up. And it crosses through the x-axis at 2 and at 3. And so if we want this exponential, if we want this expression x squared minus 5x plus 6 to be greater than 0, then either x needs to be larger than 3 or x needs to be less than 2. So if we're thinking about the domain then, it should be everything up to positive 2 together with everything after 3. I'm not including the 2 or the 3 because those would be values of x that make the inside of my log equal to 0. And remember, for a logarithm to be defined, the inside needs to be strictly greater than 0, not equal to. Log of something, log base anything of 0 is always undefined. So that means that the domain for this function, y equals log base 2 of x squared minus 5x plus 6, is that interval of everything up to 2 together with everybody after 3.